much. Thanks everybody for sticking around. It's great to be back. I think I gave my job market talk, like my mock talk for the job market in one of these rooms. So it's nice to be back in this place. This is a project about demand estimation. So let me start by defining demand estimation. So what I mean by demand estimation is a set of tools that we use to understand how people choose among different options. So for example, take tablets. This is one of the categories that we're going to be looking at in the data. How does the demand for one tablet, let's say iPad 9, change as the price of a competitor tablet, let's say Fire 7, changes? How much does it, let's say, increase as the price of Fire 7 goes up? Why do we care about this? Well, if you're the manufacturers of these tablets, if you're Apple or Amazon, the manufacturers of iPad and Fire, then obviously you're faced with the question of how should I price these products? And so you're interested in what would happen if my competitors change their price, and therefore how should I respond as a reaction? Similarly, if you're a retailer selling these electronics, you also need to worry about what's the optimal prices, what are the optimal prices for your products. So for example, take the case of Apple. If I realize that my demand doesn't really change regardless of what Fire 7 is priced at, regardless of what Amazon is doing, then I might learn that I'm kind of insulated from competition from Amazon, and I might be able to even charge a higher price as a result. And of course, this is of interest for people like myself who are researchers in marketing and economics, because demand estimation is really sort of understanding how people choose among options is a building block for many subsequent analyses. So if we're interested in the effect of a tariff or of a tax or a merger between two firms, we're going to need to answer questions like this. How do people substitute among products as a stepping stone towards answering this question? So let me start by giving you an example of a bad model, right? So a model that does not do a good job at answering this question. And I'll use this a little bit as a straw man to then show how we can improve on this. So a bad model, and this is, by the way, a model that for those who have estimated models like this is actually still quite common in the literature. It's a loaded model, though for those who are familiar with this. A bad model would say when the price of Fire 7 goes up by 1%, what happens to the demand of other products, other tablets in the market, is essentially their demand goes up, which makes sense, right? So the competitor price goes up, the other competitors benefit from this, they tend to sell more. But a bad model would say, well, their demand is going to go up by exactly the same amount. So we have around a 0.2% increase in demand for all other tablets in the market, regardless of what they look like, whether or not they're similar to the tablet that we're talking about, which is Fire 7. So here, for example, I have a Fire 8, which is not that different from Fire 7. The demand would go up by 0.2%, but also Fire 8 Kids, which is arguably a very different product. It's targeted towards a different kind of customers. Demand would also go up by the same amount. So this is a model that would not do very well. If you price based on this model, you're probably going to lose a lot of money. So you don't want to use this model for answering your question. Unrealistic. So how do we improve on this? Well, let me give you a quick version of what the literature does, how people have solved this problem, and then I'm going to talk about how we propose an alternative method. So the standard approach to answering this question is to say, well, these tablets are not all the same. So here I have Fire 7, which is the focal tablet that I'm focusing on. I'm changing the price of that by increasing the price of that by 1% and seeing how demand for other tablets change. And so we can look at the characteristics of these tablets. We can look at their prices, at their memory, and whether or not they're kid-friendly, and learn, for example, that Fire 7 is actually not that different from an iPad. It has a similar, or actually same memory, similar price, and it's also not geared towards kids. And instead, it's quite different than Fire 8, which is a different type of product, has much lower memory, and it's targeted towards kids. So if we look at the product characteristics, we can collect data, create a data set of the characteristics of these products, in this case, memory, whether they're kid-friendly or not, and price, and learn that maybe the people who tend to like Fire 7 also tend to like iPad 10, right? That these two products are kind of considered as closer to each other in the product space by consumers relative to, let's say, Fire 7 and Fire 8 Kids. And if we do this, then a model like this would tell us correctly that as the price of Fire 7 goes up, we would expect more people to switch to an iPad 10, which is a relatively similar product, relative to Fire 8 Kids, which is quite a different product. So this is the kind of predominant approach in demand estimation right now. So basically collecting data on product characteristics and using this data to understand how people switch from one product to the other as prices vary. Let me tell you a few limitations of this approach and which motivate our paper. This approach is hard to scale in the sense that if you're looking at different categories, you need to, for each category of product, you need to think about what the relevant characteristics are, right? So here I gave you the example of tablets, and we looked at memory, price, whether or not they're kid-friendly. But you can think of, if I want to model demand for toothpaste, I would need to collect a very different set of characteristics. I need to think about what the flavor is, whether they have whitening properties or not. And so for each category, I need to kind of tailor my approach and make a judgment call as to what the relevant characteristics are. And so this is, if we are interested in modeling demand across many different categories, this is not going to be very scalable, and it's going to require a lot of sort of hand-holding. Second, this approach is not going to capture hard-to-code characteristics. So if we're looking at things like aesthetic quality of a product, so particularly important for things like clothing or art or obviously music, this approach that is based on sort of physical characteristics of the product and sort of hard-coded characteristics of the product is going to be hard to apply. And finally, this is more for the people who actually use these models in their research or actually run them themselves. This is computationally tricky. So if you want to run this model on your computer, anyone who has tried to estimate a mixed logit model knows that it can be computationally challenging and can take a lot of work to actually finish running. So what we propose in this paper is a complementary method, an alternative method to estimate demand for different products that combines kind of the economic insights that we want to bring to bear for this question together with machine learning. And so we're going to do this in two steps. In the first step, we're going to use machine learning models to extract a measure of how similar products are from a range of data sources. So product images is going to be an important one. So we're going to look at how similar two products look in terms of their visuals. Product descriptions, we're going to look at the text. Think of an Amazon description of a product on the product page. Reviews, we can look at how customers talk about products. Do they talk about two products in a similar way? Do they say they're similar versus do they say they're very different from each other? And I should say we also have thought a little bit about using some Gen AI here because no talk these days would be complete without a reference to this. And we could think, although I'm not going to present results on this today, we could even think about asking ChatGPT, like tell me how similar these two products are, how closely related they are. So this is the first step, and then in the second step, we're going to input these similarities. So the first step is going to give us a measure of how close two products are in the product space, and then we're going to input these measures of similarities into a model of demand, which is where we bring the economics part to bear. All right, so let me start from step one. How do we measure product similarities? Let me tell you a little bit about the data that we use. We obtain price and purchase data from a data set called ComScore, where we essentially can see people's browsing activities, essentially anything that they browse. These are a panel of people who agreed to do this, obviously, and are aware they're being tracked. And we focus on their purchases on Amazon.com. As you might know, Amazon is not especially sort of prone to sharing their data. So we had to kind of create our data set via ComScore. We couldn't partner directly with Amazon. But we have been able to collect sort of this type of information via ComScore. We're going to look at, for this, the results I'll present today, we're going to look at 4 categories of electronics. And we're going to focus on products that have at least 15 purchases, so that are purchased relatively frequently in the data. This is the first source of data, and then we are going to pair it with data from what I'm going to call unstructured data, so data on text and images about the products to measure how similar different products are. And these are scraped directly from Amazon. And again, here Amazon is trying to make our life a little bit hard, meaning that we wrote a code that essentially systematically goes to Amazon product pages and downloads images and text. Turns out if you do that too quickly, Amazon kind of blocks you from the website because they really don't want people to scrape their website. And so we had to write a code that essentially does this in a smart way where it mimics human behavior. And you have the code kind of moving the mouse, hovering over different products and clicking at time intervals that feel human, although it's a computer. So these are the data sources. And let me show you exactly sort of the kind of data that we download, that we scrape. So for example, for Fire 7, we have, we download the main image that shows up on Amazon. We download or we scrape the titles, which often, as you can see here, kind of contain information about the product, and also product descriptions. And it's not shown here, but we also download reviews and Q&As. So on Amazon, you can ask questions about the product, and they're going to find answers on the product page. So this is the data that we get. How do we process the data? So the general philosophy that we're going to approach is we're not going to reinvent the wheel. We're essentially going to take off-the-shelf methods from our colleagues in computer science that have done a lot of work on this and have developed methods that have been proven to perform pretty well or very well at capturing similarity in the product space. So we're going to use models that have been pre-trained on large data sets, on millions of images or text. And also, these models are a little bit of a black box, so we don't really know which one a priori is going to perform better. So our strategy is to try just a number of them and seeing which models perform better. So we're going to try different machine learning models and also different data sources, right? So we're going to apply our approach to text and so product descriptions, reviews, images, and so forth. And we're going to essentially run a racehorse and see which one does better at predicting consumer choices. We have a more kind of, in the interest of time, I won't talk about this, but to choose really among all of these different options, all of these different data sources and ML methods, we're going to run a greedy algorithm that formally sort of picks the one that does the best, has the best performance. Happy to talk about this offline. So let me start by images. I'm going to talk a little bit about images and then talk about text. So for images, we use models that are geared towards image classification. So these are algorithms that have been shown to perform very well. They've won competitions where the task is to classify images, right? So is this a dog or is this a cat? That would be the kind of task that these algorithms are trained on. And formally, these are deep neural nets. So you might have heard this term before. These are sort of pretty large models that try to essentially understand from an image what kind of image this is again. Is this a dog or is this a cat? Well, we slightly tweak these models because our question is not classification. We're not interested in is this a dog or is this a cat. We're interested in how similar are these two products, right? So what we do is essentially we remove the last part of the model, the last layer, technically, of the neural net, which does the classification part, and are left with a numerical representation of the product, a vector. So imagine a list of numbers that we can then use to measure how similar two products are, right? If the two numbers in the space of these embeddings, of these vectors that we get are pretty close, we're going to say the products are similar. And if the two products in the space of embeddings are far, we're going to say the two products are not very similar. So visually, this is what we do. Here, you can start from the image, in this case, of a car. The model, you can think of this as kind of doing a dimension reduction. You starting from a very complicated object, which is an image with many, many pixels, and it's kind of collapsing it down to a smaller dimensional object. And we're going to remove the last layer, which is, again, the classification step, and really use this intermediate output, which is what it's called the embedding, to measure similarity. So this is for images. What about text? For text, we actually do a very similar thing. We start so we have different sources of data, as I mentioned. And we start from very simple models called bag of words models, which essentially count how much overlap there is among two sources of text in terms of the co-occurrence of the same words. So for example, if two texts, if two reviews or two product descriptions have both the words 16 gigabytes for memory, that is going to get picked up by the model. And then we use more complicated models that also allow for context. So they're not just counting how often words show up in text, but also try to infer meaning and context from the text. So this is the first step. So the first step is we scrape data from Amazon on images and text. We process this data using machine learning, essentially. This gives us a measure of how similar two products are, right, in the space of images, in the space of text, reviews, descriptions, and so forth. And the second step is to combine this with economics, like to bring this data to bear and combine it with an economic model of how consumers behave. And so this is what we propose. We propose a model. I'm not going to go into any detail. It's called a pairwise combinatorial logit model, which has been used before in the literature. But think of this as a choice model. And very, very intuitively, what this says is the utility that consumers get from a product is going to be such that two products that are similar to each other, for example, Fire 7 and iPad 10 in this case, are going to tend to have utilities that are close to each other, that are more correlated with each other relative to, let's say, Fire 7 and Fire 8 kits, right? So people who have a preference for Fire 7, who tend to like Fire 7, because these products look similar and also maybe their descriptions are quite similar, the model is going to say they're going to have the people who like Fire 7 are also going to tend to like iPad 10 and maybe don't like Fire 8 kids as much. And therefore, when the price of, let's say, Fire 7 is going to go up, people are going to tend to switch to iPad 10 more often than Fire 8 kits, because that's just a different product that tends to cater to different kinds of consumers. So this kind of delivers the kind of substitution patterns, switching patterns that are intuitive and that we would want to represent. So let me show you some results. First, some measure of model fit. So here, basically, we are running a horse race among different models and different sources of data. So each cluster of bars is a different source of data: images, titles, descriptions, Q&As, and reviews. And for each of them, we're going to use different ways of processing this data. So all of these are machine learning models that have been proposed to process image and text data. And so here, the way to read this chart is higher means better. So a higher bar means better fit of the data. The model is capturing the data more successfully. So here you can see that images actually win the race. So they tend to do better than text, to different degrees depending on how we process the data. And similarly, we have a kind of a mixed picture for text, where titles tend to do better than, for example, reviews. Definitely not the best performers. And so this kind of validates our idea of trying a few different things and seeing essentially what sticks. So here we learned that models that use images as sources tend to do better. And we're a little bit surprised by this initially, because this is a product category. This is not clothing, or this is not books or music, where you could imagine that the image might be very important. This is a product category where a description should be quite informative, right? Because it just gives you the specifications of the iPad versus of the Fire 7. But one potential reason, this is something we want to speculate or think a little bit more about, is that if you look at these, let's see if I can zoom on this. Whoops. If you look at these descriptions or these images, the images actually contain a lot of text and contain a lot of information about the product itself, right? And sort of the product characteristics. So one hypothesis here is that the image processing is actually capturing some information, not just about the looks, but also about the actual characteristics of the product and how similar two products are in terms of their specifications. Let me quickly go back here and show you then some results in terms of the substitution patterns. So remember the first plot that I showed you, where all the bars have the same height, right? That was the bad model that I presented to you, that essentially said, regardless of the tablet, the tablet is going to have the same kind of demand response to a change in the price of Fire 7. Well, here we're getting something that's starting to look more realistic, right? So what happens if the price of Fire 7 goes up by 1%? All the demand for the other products goes up, which is what we would expect, but they go up to differential degrees, right? So for example, Fire 8, HD 8 over here, whoops, here we go. Fire HD 8 is the one that tends to have the strongest response. So for 1% increase in the price of Fire 7, demand for Fire 8 goes up by 0.35%, which is perhaps realistic, because these two products are quite similar. One is the next version of the other. And instead, you can see that, for example, Fire 8 Kids over here tends to not respond much to a change in price of Fire 7, again, because these are just different products. One is catered towards adults, one is catered towards kids. And so the model is learning this feature from the image data in this case, that we have fed into the model. All right, I think I'm going to conclude very quickly and then open it up to questions if there are any. But let me just summarize what we've done so far. We have proposed a way to integrate text and image data into a demand model. And so this combines two pieces. One is the machine learning part, so processing images and text to extract a measure of how similar two products are, any two pairs of products are, and then inputting this into an economic model of demand. So combining machine learning with economics. Why is this helpful? It's a little bit more scalable, we argue, than standard methods, because as long as you have data on the images or products images, on reviews, on descriptions, this approach can be used. You don't need to commit, you don't need to make a decision as to what characteristics matter for toothpaste versus tablets versus clickers and versus whatever product category you're focused on. It is sort of has the ability to capture unobserved quality or sort of visual characteristics, aesthetic qualities that are otherwise maybe hard to pick with the standard methods. And what we're trying to do next is this is work in progress, we're trying to actually validate this approach using an experiment. So we're going to have people choose among a set of products. We're actually working with ebooks in our experiment. And then we remove the product that they chose and we ask them to choose again. And then, so we're essentially seeing switching patterns in the experiment. And what we're hoping to find is that this model does a better job at predicting the second choices that people will make relative to competing models. So I'm going to wrap this up and happy to take questions.